Okay, in the last video, we looked at the mathematical modeling of the electric field, and now we're going to look at a new way of modeling it and sort of thinking about a visual model, how we can create a visual model. You know, if you think about some of the models we looked at in the past, like the free body diagrams or vector diagrams even, we frequently are going to be using arrows as a way of representing both the direction of something, but then also the strength of the thing, whatever it is. Now, in order for you to see this new way of looking at things, we're going to kind of look at things in the old way by doing a free body diagrams, and I think that you'll see how this idea of electric field lines evolved as kind of in the imagination of Michael Faraday. You know, again, this was a great experimental physicist. Not super great at the math. That was really other people who worked out the mathematical meaning of his experiments, but just really had a lot of intuition and just great insights into how things work in the physical world. Part of what makes experimentalists good at their job is that they just can make things work. They can just figure out how to get the experiment to work correctly so that they can see what it is that they're trying to look at. So in order for you to visualize what we're talking about here, I'm going to place a large positively charged object here, and then what I'm going to do is I'm going to place a bunch of test charges. So if you remember in the last video, we talked about calculating the electric field strength by placing small test charges. So I'm going to place small test charges. These guys are very tiny. Okay, so I have a lot of little positive test charges. Each of these guys is a positive test charge that has been placed in the vicinity of this electric field. Now, let's just imagine what would the free body diagram look like for these little test charges. Well, each of these guys would feel a force. They would feel a repulsive force. So that force would point away. And if you were very close to this, so if you're this charge that was closest to it, that would be a very large force. So I'm going to draw very large arrows on these ones that are closest. So these guys experience very large force. The force points away, points directly out from the center of the positive charge, because these two charges would repel each other. Positive charge and a positive charge are going to repel each other. If you're looking at the forces way out here, these guys would also repel each other, but that force would be teeny tiny little force for these guys out here. Okay, and you can imagine that if we were to look at all the charges in between, we'd see like somewhere in between, right? So as we look at this one, we would see that, yeah, the arrow is not quite as long, but still pretty significant force acting on this guy. And as we move farther and farther away, we're going to find that these arrows get smaller and smaller and smaller. Right, so you can kind of see when you look at this picture kind of how Faraday maybe came up with the idea of electric field lines. Now, these are not field lines. I have not drawn the field lines yet. I just simply drew the force acting on little positive test charges that have been placed all over to see what does the shape of the electric field look like. And look, this is what it looks like. It looks like the spokes on a wheel. You can imagine all these things point out radially, directly away from the center of the object. No matter which one that I'm looking at, you will see that the force lines up along a line that is directly radial, meaning that it comes either directly into or out from some central region. And I think that this is really a lot of what kind of inspired Faraday to draw the field lines, which are kind of, I feel like, based on this idea, but are representing it in a different way. So here, the length of these lines represents the strength of the force. Now, in the new field lines we're going to draw, that's not going to be the way we're going to represent strong electric fields. We're not going to use the length of the line. So that's why this is really truly a different thing. This is something we've already done. These are just free body diagrams, these being the only significant force acting on these test charges. Now we're going to draw something truly new. And in order to do that, we need to think about what are the rules that Faraday came up with for how electric field lines work. And by the way, these rules are used for all kinds of other fields, like magnetic field or gravitational field. People went back and said, hey, this is a great idea. Let's think about gravitational field in terms of these field lines that Faraday is imagining. And while initially many people were resistant to his idea of field lines, today field lines are one of the most easily absorbed ways of thinking about how the electric field acts between two charged objects. So let's go over the rules for the field lines, and you make sure that you write these in your notes, of course. So the first rule, and this is a rule that is true for all field lines that you would experience, and that is that field lines never cross each other. So when field lines start to come near each other, they're going to start to bend or to turn to avoid each other so that they never cross each other. It was kind of an arbitrary decision, but it had to be decided, well, where do the field lines start? But look, we've already said that the test charge is based on a positive charge. And look at the way that the force acts on positive charges when they're near another positive charge. They point away. They point radially away. So Faraday said, I'm going to start the field lines on the positive charges because look, doesn't it look like these arrows all originate with that charged object up here? They seem to originate from the positively charged object because of the way the electric field is defined. And then they're going to end on a negative. So imagine that I had a negative charge over here. I put a large negative charge over here. What would happen to all of these arrows? Well, all these arrows would start to point down towards the negative charge because they would be attracted to that negative charge. So you can imagine how the negative charge looks very similar to the positive charge, except all the arrows point in exactly the opposite direction. So this is probably partially what inspired the idea that if you start the field lines on the positive charge, that means that they therefore must end on the negative charge. And then the last rule is that the field lines are always going to be perpendicular to any conducting surface. That is to say that they are going to exit the surface radially or pointing straight outward like this. Okay, so make sure you write the rules down. If you need to pause the video because I'm about to move on to starting to draw these, we're going to look at 6 different pictures of different ways of thinking about the charge, but using all of these rules for electric field lines, and we'll show you how they work out in the practical world. So let's start with the first, the positive charge first, because that's certainly the easiest one to think about. It's consistent with the picture that we just initially drew. But again, this is a new picture, okay? It's not the same as the picture that I drew the force. I'm not drawing the force now. Now I'm drawing the electric field lines. And the rules are that, first of all, field lines are perpendicular to conducting surfaces. So that means that all the field lines are going to exit as though they were the spokes of a wheel. They're going to point outward from the positive charge because electric field lines start on the positive charges. Now we can draw as many or as few field lines as we want to, but of course the more lines that I draw on this object, the larger I'm saying that the charge is. More lines equals more charge. More lines equals more electric field strength. So in this way of modeling the electric field, we're not looking at the length of the arrows as a way of modeling what is the strength of the field. We're looking at how many lines are there. So for example, let's say that I take and I make a loop right here, and I just make a big loop like this right here. Okay? Now there would be 3 field lines going through that loop. So when the field lines are close, that means a strong field. Okay, where the field lines are close to each other, the electric field is very strong. And where the field lines are far apart, that means the field is weak. Okay, so this is a little bit different idea than the free body way of thinking about forces. And again, I'm not drawing the force. These are not force lines. These are electric field lines showing the direction, and then based on the concentration. So here, very concentrated, but if I make the same size circle up here, you notice I don't catch any of the field lines anymore. So now the field is much weaker. So because of the way the field lines point, you can see they just naturally become weaker as they move farther away. And we've already seen that with the mathematical model because the field gets weaker as the square of the distance. So the farther you get away, the weaker the field is. And these drawings actually show exactly what the equation says should happen. If we were to draw the negative charge, well, that would look exactly the same as the positive charge. So this should be a very quick drawing to make. It looks exactly the same. All the lines point radially as though they were the spokes of a bike. The only difference being between the positive and the negative picture is that the field lines are ending on the negative rather than starting on it. So all of my arrows should point inward. But otherwise, the pictures would be exactly identical between the negative charge and between the positive charge. Exactly the same, except the arrows point in the opposite direction. Now, what happens when you bring these particles together? Like let's say, for example, I brought 2 positive charges together, or two negative charges? Or what if I brought a positive and a negative together? What would happen to the field lines? Because they have to follow these rules and they cannot cross each other. So how do they adjust when another charge is nearby to avoid crossing the field lines of other objects? So let's take a look at that situation. And we'll start with light charges. We could use either positive or negative because, again, the pictures are more or less exactly the same, just the direction of the arrows a little bit different. But we'll say in this particular example that we have two positive charges. So these might be two small pith balls that have become charged. There's obviously some field lines that are probably not going to be affected at all, and that is the field lines that point directly away this way. These field lines are not going to cross anybody else. They really have nothing to worry about. It's all the other field lines. So there are field lines that should be coming like this, coming out from these positive, and then obviously there's going to be a problem because those guys are going to cross. So here's what's going to happen to those field lines that exit the positive charge in a direction towards the other charge. They are going to be very sharply bent. And they are going to turn until they are parallel, like this. Okay, and I'm not going to draw this because I don't want you to draw the wrong thing. They turn until they become parallel, and then they just continue like that because now they're not going to cross. There's no reason for them to continue turning. So don't draw that in your pictures. Don't draw the field lines turning until they turn away from each other. That's not the way that they look. Like, just imagine you're getting on the highway. Okay, you're coming down on an on-ramp on the highway, and you're merging. So you're turning. Once you get into the lane, do you keep turning? No, you don't keep turning. That would be crazy. You don't drive off the road into the ditch. You turn and turn and turn and turn until you become parallel. And once you become parallel, there's no longer any danger that you're going to cross somebody else's path. So you don't need to do anything anymore. And that is the same thing that the field lines are going to do. They will bend and bend and bend until they become parallel. And then the field lines will simply go straight from that point forward. So let me draw in the field lines that are on the top up here. Okay, so what we end up with is very sharply turned lines, lines that are bending away from each other. Now, those lines, as they get turned like that, they're going to push on the other lines, and the other lines are going to move to accommodate them also. Now, I just want you to think about where the field line is going to be most bent, most disturbed, is going to be in between, where the field lines are going directly towards each other. The other field lines will also be curved, but their curve will be substantially less. So if you notice, this line that I just drew is much less curved than this one, and this one is much less curved than this one. So as you move away from the point where the field lines are interacting, you'll see that they are curved. Essentially, all the field lines have been pushed back like this, but ultimately the field lines become less and less curved as you move away because this guy wasn't going to run into anybody anyways. So again, very sharply curved lines if you're near on the side that is facing the other charge, but as you move around to the back side, you're going to find that these guys are much less, the charge is much less. Okay, and I'm going to finish the picture by completing on this side. Again, very sharply curved lines, less sharply curved lines. Sharp curve, gentle curve. Okay, so this is what the picture looks like for the electric field lines around two light charges, two positive charges. Now, if you just think about, what about here in the middle? I mean, there's field lines everywhere. I haven't drawn them everywhere, but there are field lines. There would be more field lines here and here. But right here, how could a field line get in there and not cross each other? There's no way to do that. So there is no E field here. It's a very interesting thing of bringing light charges together. You actually get a little null spot, a little dead spot, where there are no electric field lines. So that's what the picture looks like for light charges. They bend away from each other to avoid running into the lines coming from the other guy. What if it was what they were looking for, though? What if it was a positive charge matched up with a negative charge? One that wants to start the field lines and one that wants to end the field lines. Well, obviously, one of the field lines that would be really clear is this one. One of the field lines will just go directly across. But then you also have field lines that start like this and start like this. What happens to those field lines? Well, they are looking for a negative. You know, essentially the way we talk about the electric field lines is that they are negative seeking. They are seeking a negative charge. No matter how that field line originated, it is seeking a negative charge to end on. So in this case, what's going to happen is these guys are going to bend in order to come over and meet that charge on the other side, the negative charge. Again, always entering perpendicular to the surface. Leaving the surface perpendicular and entering the surface perpendicular. We have the charges that were, the field lines that were coming out here. Those field lines are going to bend and come all the way over. And I can't draw every single field line on this because the piece of paper just isn't big enough to be able to pull this off. But you can see that you could imagine these field lines continuing up around the paper, coming all the way around, and then coming over here to the negative end of the negative charge. The field lines should make a consistent picture. Everybody's curving in the same direction. And so oftentimes what I see is people draw the curve going in the other direction over here, but that doesn't really make sense. Remember, the field line wants to go over. They want to be connected together. They're not trying to avoid each other. They actually like each other in this situation. So like charges, opposite charges. Okay, two last things to look at for the shape of electric fields is what happens with hollow spheres. I'm going to draw a very large sphere. And then I'm going to redraw this hollow. So I'm going to draw the sphere over here again, but I just want to look at it up close. If we could look at the surface of a hollow sphere and something that we place charges on, what we would see is that there would be some field lines that want to go straight away. Okay, that field line has no issue. It's going directly away. It's not going to cross anybody else's field lines. The question is, what about all the other field lines? What about the one that was going to go out this way? Or what about the one that was going to go this way? Or what about the ones that were going to go inside the sphere, towards the inside of the sphere? What's going to happen to them? Well, obviously, with all these other charges on either side of them, to his left or his right, all of this guy's field lines are going to be bent like this. And what I mean by all the field lines is, I mean, even the ones that were pointed inward will bend all the way back around and point all the way back in the opposite direction. No field lines will come in here. And the reason for that is because there's no way for a field line to come into the sphere and then exit the sphere without crossing somebody else's field line on the other side or even on the near side. There is just no way for a field line to be drawn in here. And remember, field lines can't just go in and stop. They don't just end. They must end on a negatively charged object. So that field line with no negative charged object inside this sphere, the field lines cannot go on the inside without crossing each other. So all the field lines are going to point outward. So ultimately, what would happen if we drew a large sphere and we put positive charge along the outside of it is that we would see the field lines pointing directly away. Just as though this was a point charge, the sphere on the outside will seem pretty much exactly the same as a point charge would be if we had just a very small charged object with all of its field lines pointing directly out. And inside, there would be no E field. Okay, if you thought about this in terms of a graph of what does it look like if we were to measure the electric field versus the radius, well, if you imagine that there was a special spot here, big R, and big R is the radius of this sphere that we've drawn, well, essentially there would be nothing happening until you got to R. Okay, then as soon as you get to R, you're going to see the electric field is going to jump up. We could calculate it by using the equation KQ over R squared. It's going to jump up to some value which is equal to KQ over big R squared. Okay, that is the most intense that the electric field can be. That's going to be right here on the very surface of this, not on the inside, but on the outside. The electric field is going to be incredibly intense. A lot of charge there, a lot of electric field line, very strong electric field. Now, what's going to happen to it? Well, it's an inverse square law. So what's going to happen to it is the field is going to rapidly drop off and then kind of asymptotically approach zero as you move very, very far away from this object. So no electric field until you get to big R, and then it jumps up, and then it's going to fall away. Now notice the R that I'm using is all the way back to the center of the sphere, because once I get to this surface, then I can treat the entire rest of the charge as though it's concentrated at the center. And I know this is a little bit of a weird thing to think about, but imagine you're this charge here on this side, and you say, well, you know, he's very close to these charges on either side of him. I mean, way closer than the radius, for sure. But what about the charges on the other side? How far away are those charges? Well, those charges are 2 times this radius away. So you have some charges that are basically right next to it. They're almost 0 distance away. And you have some charges that are way over on the other side. They're at a distance of about 2r. So what is the average distance? The average distance would be just the radius. So once we get to the surface, okay, we just treat the charge as though all the charge was concentrated at the center, even though that's not really what's happening. The equation will give us the same answer as if we imagine that all of this charge was concentrated at the center, but we only do that once we get outside of the sphere. Inside the sphere, it's super easy. There is no electric field. There's nothing to calculate. You don't need any equation. You just need to be able to explain why are there no electric field lines inside. And again, that has to do with following the rules for electric field lines. Let's look at one last example. This last example is a kind of similar thing, but sort of in the opposite. Instead of having a single charge, we're actually going to have 2 charges. So we have some positive charges, and then we're going to put an equal number of negative charges on the opposite side. So these are 2 charged, so this should say charged plates. 2 charged plates. So essentially what I've done is I've taken some of the negatives from this plate and I've pulled them off and then put them onto this plate. And what that did was create 2 charged plates, 1 positive plate, 1 negative plate. Now obviously the field lines want to do this. They want to go across to the negatives. This is their goal. The goal is for the field lines to end. So first of all, none of the field lines are going to go outward from the charged plates. All the field lines are going to be concentrated here in between. All the field lines will be drawn in between the plates. Now another thing about this is, remember, the field lines can't go out like this because they're going to cross the field lines of the people next to them. So what you're going to see is that the field lines are going to be, 1, perfectly parallel to each other. That means that the field is uniform. The fact that the field lines don't get closer or further means that the strength of the field is not changing no matter how far away to the left or to the right that you move. So I am intentionally trying to draw these roughly equally spaced. Not doing a great job of it, but trying to draw these all evenly spaced. And then the question is, what happens at the end? Well, this guy on the end, notice there's no charge to the right of the end here. So this field line does bow outward just a little bit, but he still sees where he wants to go, which is to the negatively charged plate. Same thing on this side over here. This has a very fancy name. It's called the end effect because it happens at the end. And what happens at the end is that the field is not actually perfectly uniform. The field is a little less strong than it is here in the middle. What is it that tells me that this field is uniform? Parallel lines means uniform field. So because the lines are not becoming more concentrated or less concentrated, that means that the field strength is not changing. So that's, if you want to show that a field is uniform, you want to draw the lines parallel to each other because that will ensure that the field is not having more field lines or less field lines as I move from one point on the plate either up or down this way, or if I even move left to right, so long as I stay away from the ends where there is nobody to force this line to stay parallel.